Assalamualaikum and hello everyone and welcome to our video presentation. My name is Muhammad Firas Hasanuddin bin Fazil and I'm representing my group of 5 members who are currently studying at University Technology Mara UiTM Tapa. Let me introduce you to the amazing member of ours. So the first one is Adib Hariri, always reliable and brings so much energy to our work. Next we have Iman Zulaika, a creative thinker who always has innovative idea. Here Nur Ain Kisina, who ensure everything is organized and on track. Meet Nur Alia Shamimi, the communicator of our team, connecting us with their great interpersonal skills. And finally, Marisa always give positive impact to our teams. We are enrolled in the CHM256 course and today we are excited to share with you an interesting topic, thin layer chromatography in sunscreen. Through this presentation, we will explore how thin layer chromatography is applied to analyze the component in sunscreen, providing insight into its effectiveness and formulation. Let's get started and dive into the science behind it. Hi everyone, my name is Muhammad Firdaus Hasanuddin bin Fazil. Today I'm going to talk about thin layer chromatography in a sunscreen. So first, did you know that science is all around us, from protecting your skin under the sun to separating complex mixture in a lab? Today, we're going to talk two fascinating concepts: why sunscreen is essential and how chromatography helps us uncover the hidden components in the mixture. Let's dive right in. So first, what is chromatography? It is a method scientists use to separate mixture into their individual components. Here how it works. There are two main parts, the stationary phase, which is stay in the place, and the mobile phase, which is move the components of the mixture. Interact differently with this phase. Some move faster with the mobile phase, while the others slow down by the stationary phase. This difference allows us to separate and identify the components in the mixture. One type of chromatography is a thin layer chromatography or TLC. It is simple, fast, and affordable. Here how it works. We use a sheet coated with an absorbent material like silica gel. First, we spot the sample on the sheet and dip it into solvent. As the solvent moves up to the sheet, it separates the components of the mixture into spots. Each spot can be measured using retention factor or RF. Calculate as the distance traveled by the sample divided by the distance traveled by the solvent. Factor like the solvent system, temperature, and absorbent material affect the result. TLC is an essential tool in the science, and the best part, it's easy to do and highly effective for analyzing mixture. Thank you.
Theory of TLC. Principle. Stationary phase. A thin layer of adsorbent material, silica gel or alumina, act as a medium for the separation of components. The adsorbent interact with the compounds in the mixture. Mobile phase. A solvent that moves through the stationary phase via capillary action helps to transport the sample along the TLC plate. Separation. As the solvent moves up the plate, the different components in the sample mixture interact differently. This differential migration leads to the separation of compounds can be observed on the TLC plate. Retention factor RF. RF value is a ratio used to characterize the movement of compounds on the TLC plate. Here are 6 key techniques of procedure involved in TLC. First, preparing the plate, clean and dry the TLC plate, then activate it if necessary. Second, spotting the sample, apply a small amount of the sample above the solvent level using a capillary tube. Third, developing the plate. Place the plate in a developing chamber with solvent to separate components by capillary action. Next, visualizing the spot, use UV light or stains to observe separated spots. Next, RF calculation. Measure the distance traveled by the compound and solvent, then calculate the retention factor RF. Lastly, interpretation and comparison. Compare RF values, spot appearance with standard to identify compounds. Here are some key advantages of using TLC. First, simple and quick. TLC is a fast and straightforward method for separating and identifying compounds. Second, low cost. It requires minimal equipment and consumable, making it cost effective. Third, small sample requirement. Only small quantities of sample are needed for analysis. Next, high sensitivity. TLC can detect compounds in low concentration, especially with appropriate visualization techniques. Next, versatility. It can be used for a wide range of compounds, organic, inorganic, and mixture. Lastly, minimal solvent use. It typically uses small amounts of solvent, making it environmentally friendly and economical.
I will proceed with the methodology. First is objective. The objective is to analyze the chemical composition of sunscreen using thin layer chromatography, which is TLC. Next is list of materials. First is TLC plates, capillary tubes, beakers, pencil and ruler to mark the TLC plates, UV lamp with 254 nm, sunscreen with different SPF ratings, solvent for TLC development, which is cyclohexane, diethyl ether, and solvent for attraction, which is ethanol and methanol. Next, we proceed with the methodology preparation steps. First is sample preparation. Weigh 1 gram of each sunscreen samples, different SPF ratings. Add 5 until 10 ml of ethanol or methanol to dissolve the active ingredients. Mix thoroughly and filter the solution using a filter paper to remove insoluble components like thickener or particulates. Second is TLC preparation. Cut the TLC plates to a manageable size, which is 5 cm times 10 cm. Using a pencil, draw a baseline 1 cm from the bottom of the plates where sample will be spotted. Avoid using a pen as it can interfere with the result. Mark even spotting point along the baseline for each sunscreen samples and reference standards if available. Move to the next. The third one is selection of solvent system based on the expected polarity of sunscreen active ingredients, which is we have two for non-polar and polar components. For non-polar components, which is avobenzene and oxybenzene, we need to use ratiohexane with ethyl acetate with ratio 7:3. For polar components, which is homosalate, we need to use chloroform with methanol with ratio 9:1. Test a small batch with a few spots on a separate plate to ensure proper separation. Next is spotting the samples. We need to use a capillary tube or micropipette to transfer 1 until 2 microliter of each sunscreen solution onto the marked baseline spots. Second one is allow the spots to dry for a few seconds between application to avoid smudging. If needed, we need to repeat spotting on the same spot to concentrate the samples, ensuring the spots remain small 2 until 3 micrometer in diameter. We move to development steps. First is develop the plate. Place the TLC plate upright in the chamber with the baseline above the solvent level. Close the lid and allow the solvent to rise until it's 1 until 2 cm from the top. Remove the plate and immediately mark the solvent front with a pencil. The second one is visualization of spot. Under the UV light, we need to observe the TLC plate under a UV lamp, which is 254 nm, and mark the location of the fluorescence or UV active spots. Next, using visualization reagent, spray the TLC plates with iodine vapor, ninhydrine, or any saldehyde reagent, depending on the expected compound. Heat the plate gently if required and observe the appearance of spots. The last step is analyzation steps. First is analyze. Measure the distance each spot and the solvent front traveled. Calculate the RF value for each spot, which is RF equal to distance traveled by the spots. Next is compare SPF samples. Compare the number, intensity, and RF value of the spots from different SPF ratings to determine difference in active ingredient composition.
As for retention factor, after a separation, individual compounds appear as vertically separated spots. Each spot has a retention factor RF that is proportional to the distance moved over the entire distance covered by the solvent. Each chemical has a unique RF value. Compounds with greater RF value are less polar because they do not adhere as well to the stationary phase as more polar compounds with lower RF values. For the formula, RF is equal to distance traveled by substance over distance traveled by solvent. In the example, distance traveled by substance is 2.1 cm and distance traveled by solvent is 2.8 cm. In the calculation, we will get 0.75. For the factors affecting RF values, it can be from layer thickness, moisture on the TLC plate, vessel saturation, temperature, mobile phase depth, sample size, solvent characteristic. While these parameters typically rise RF values, thicker layers may reduce RF values as the mobile phase travels slower.
Hello everyone, today we are diving into the world of sunscreen chemistry using technique called thin layer chromatography or TLC. This powerful method allows us to separate and analyze the active ingredients in different sunscreens. Let's walk through two scenarios that highlight how TLC results can tell us a sunscreen chemical composition. Result A with the same or identical composition. In result A, we observe that all the dots on the TLC plate appear in the same position for each sunscreen sample. This observation leads us to conclude that these sunscreens have identical chemical compositions. Why is this important? The retention factor or RF value is the ratio of how far a compound travels on the TLC plate compared to the solvent. Identical RF value means the same active ingredients are present in each sample and in similar proportions. So the conclusion is, it's common for sunscreen from different brands to use the same formulation, even if they have different packaging, marketing, price points, so the underlying chemical structure can be nearly identical. This may include popular UV filtering agents like homosalate, which is used for UVB protection, autocryocline, which stabilizes avobenzone and absorbs UV ray, and then avobenzone, providing broad spectrum UVA protection. Next, for result B, which is different composition. In result B, things get more interesting. Here, the pattern of spot is different. The sunscreen on the left shows a different set of dots compared to the two on the right. What does this tell us? The sunscreen on the left has a different combination of active ingredients or proportions. The distinct RF value indicate a variation in the chemicals used for UV protection. For example, the sunscreen on the left may contain zinc oxide or titanium dioxide, which are physical blockers that reflect and scatter UV rays. In contrast, the sunscreen on the right might use avobenzone, oxybenzone, or octinoxate, which are chemical filters that absorb UV radiation. Why does this matter? Different active ingredients provide different approaches to sun protection. Zinc oxide offers broad spectrum protection and is known for being stable and gentle on sensitive skin, while avobenzone is excellent for UVA protection but requires stabilizers like autocryocline to prevent degradation in sunlight. Additionally, different formulation may affect factors such as water resistance, spreadability, skin feel, and cosmetic appeal.
And so, in conclusion, higher SPF sunscreen block more UVB rays, but the difference isn't huge. For example, SPF 15 blocks 93%, while SPF 30 blocks 97%. Those sunscreen can block 100% of UV rays, and high SPF doesn't guarantee significantly better protection. UVB rays are strong even on cloudy days, but UVA rays are more affected by clouds. Researchers use thin layer chromatography, which is TLC, to study sunscreen ingredients and found most are similar, regardless of SPF or brand. However, sunscreens with zinc oxide and avobenzone behave differently and offer unique benefits. To protect your skin, apply a palm full of sunscreen and reapply every 2 hours, especially after swimming or sweating. And choose broad spectrum sunscreen to protect against both UVA and UVB rays. Remember, high SPF sunscreen don't provide total protection. Misusing them by staying in the sun longer can increase your risk of skin cancer like melanoma. Overexposure to UV rays, especially in childhood or from tanning beds, is a major cause of skin cancer. Use sunscreen properly and know its limit for better protection.